A warehouse worker is pushing a 90 kilogram crate with a force of 289 newtons. They give a speed for the crate across the warehouse floor, and then he encounters a rough horizontal section of the floor, 0.75 meters long, and there's a coefficient of kinetic friction between the crate and the floor. They say, first of all, determine the magnitude and direction of the net force acted on the crate while it's being pushed across the rough section of the floor. Alright, so I'm going to draw a free body diagram first, and I'm going to draw the guy's force pushing to the right. There's also going to be a backward force of friction, which we have to calculate. It's going to be kinetic friction, so we'll use the mu k n formula, mu k times the normal force. So let's go ahead and find the normal force of the crate. So the weight is going to be downward, and that's going to be found by mg. So take your mass of your crate, 90 kilograms, multiply that by g, and let's see what that weight is. 882 newtons. Then that makes the normal force also equal to 882 newtons. Let's calculate that kinetic friction then. It's going to be 0.355 times the 882. I get 313 newtons for that. So that tells me something. The friction here is exceeding the push. So I better modify my diagram. I need the push to be actually smaller than the friction. So is our object, do you think, going to be slowing down or speeding up? Okay, so our guy, his job right now is to put energy into the system. He does it through work of his push. But energy can also leave the system through the floor. And that'll be the work of friction, and it'll be a negative. Yeah, so the friction force wins in this situation, meaning the box is going to slow down. The net force will be found by subtracting. I'll do 289. That's this one. Force of push. And then we're going to subtract 313. And that, of course, comes from here. So our net is going to be negative. It's a negative 24 newtons. Okay, now they ask us to determine the net work done on the crate while it's being pushed over the rough section of the floor. So the distance there of the push, they claim, is 0.75 meters. In order to calculate the net work, what you need is the net force and a dot product with the displacement of the crate. What angle do the force and the displacement have in this case for this crate? Well, here's the thing. The crate goes forward. That's his delta x. Which direction is the net force? It's the opposite. So we have two vectors which are anti-parallel, or like opposed. What's the angle between them? You gotta measure like this. It's 180. So we need the magnitude of the force times the size of the displacement times the cosine of the angle between them. So what's it going to be? 24 times 0.75 times cosine of 180. I get 18.1 joules, but it's negative. Now we got to find the final speed of the crate when it gets to the end of that rough patch. You'd really want to use the work energy theorem, because even though energy is conserved in the universe, it doesn't mean it's conserved in every system. Okay, so what's our system? Just the crate. Energy is not conserved for just the crate. Some energy is coming in to the system from the guy, but a lot more is leaving the system through the floor. So we have a net loss of energy, and this is how much we lost in that rough patch. So according to the work energy theorem, you could say that your UGI plus your KI plus any non-conservative work will equal UGF plus KF. Now in this particular problem, the UGs are irrelevant because your crate is just on the ground. It's not going up in height. It's not going down in elevation either. So I wouldn't even include those terms. I'd just stick to this. Now the non-conservative work would be done by the guy and the floor. Those are both called non-conservative forces. So let's figure out how much energy the crate started with this calculation. Let's put in the loss of 18.1 joules overall here for our WNC term. And then we can do a calculation here, 1/2 mv final squared. Ultimately, we're going to be looking for this V final. So let's see, the mass of the crate was 90 kilograms. Initial speed, 0.855. Plug in your 90 kilograms again. And then just solve for V final. I think it's 0.573 meters per second. So he did slow down because he started with 0.855.